Welcome to part 2 in personal renewable energy. In this video, we will get a little deeper into the components. This is a Hydro-Quebec generating station near James Bay in northern Quebec. This is one of the many locations where the electricity is generated. The cost to produce this energy is almost zero, and the energy produced is enormous. As long as the water flows, this is a renewable source of energy. However, not all parts of the world have access to such an abundance of flowing water. These are high voltage electrical poles. Using these, Hydro-Quebec transmits electricity in the range of 44,000 volts or 44 kilovolts to 765 kilovolts. Transporting electricity at these high voltages has low losses and therefore can be distributed over very large distances. We have all seen these metal cans on hydro poles near our homes. These are transformers. They take the electricity down to 240 volts AC, which is the voltage that is fed into a North American home. The 240 volts AC is fed into an electrical panel, such as this one from a Rona hardware store in Canada. There are 4 wires that come into the house: L1 or phase 1, shown by the red wire, null or neutral, the white or shown here as a gray wire, L2 or phase 2, the black wire, and earth, shown as green. The 240 volts AC is split between the L1 and L2 phases down to 120 volts AC. An electrician connects L1, L2, null, and earth wires provided by the utility company according to code. If you want to know more about how to make proper connections, there are plenty of videos on this topic on the internet. Often you will hear that we have a 110 volt supply in North America. That's at the outlets and takes into consideration potential losses in voltage from the panel through the wires to the outlets. Some household appliances such as stoves and dryers require 240 volts AC to operate. The 240 volts is from the unsplit L1 and L2. L1 and L2 are then wired to power a section of the house such as a room or a specific appliance. The connections are fed through breakers that limit the current in case of faulty wiring. Breakers typically come in 15 and 30 amps. However, there are several different values that could be used, which is a topic for later. The nulls or returns and ground wires from all the household loads are connected to a bus bar in the panel, thereby grounding the entire box. In Europe, the voltage is not split. Typically, there is only a single load plus null and earth. The voltage between load and null is 230 volts AC. There are advantages to using 230 volts compared to 120, and it is related to loss in the cable. The losses in the cable is I squared times R. If we assume that the cable resistances are the same, then 230 squared is 52,900 and 120 squared is 14,000. The losses in the 120 volt system are over 3.5 times. This is an electrical panel from the Home Depot hardware store. This smaller panel can be connected as a sub-panel to the main panel. These smaller panels power a smaller number of loads as compared to much larger main panels, which are meant to power an entire home. Sub-panels are useful for powering remote locations from the house, such as a garage or workshop. To connect the sub-panel to the main panel, a connection is made through a breaker from the main panel. Null and earth are also connected back to the main panel. If there is L2, this also would connect to L2 back in the main panel. It's not necessary to have L1 and L2 in a sub-panel. However, in either scenario, the electrician should consider load balancing L1 and L2 back in the main panel. We also have to be careful in a sub-panel to isolate the nulls from ground. If the null is connected to the ground wire in a sub-panel, then current flows back on both the neutral and on the ground wire. With faulty wiring, it's also possible to have a live panel box, in which case you might be a path to ground. Why mention sub-panels if few have ever even heard of one? Sub-panels offer an advantage which I will discuss much later in another video. Now that we have a basic understanding of how electricity reaches your home, we can start to look at some less familiar components and concepts in renewable energy. Photovoltaic solar panels are also known as PV panels or solar panels. These panels can absorb sunlight as an energy source to generate electricity. A PV panel is actually a connected array of photovoltaic solar cells. These are the squares that you see in the panel itself. The larger panels have 60 or 72 of these cells. Each of these individual cells generates about 0.5 volts, which means that a 60 cell panel will operate at approximately 30 volts, 60 cells times 0.5 volts, and a 72 cell panel operates at around 36 volts or 72 times 0.5 volts. The typical output power that you can expect from medium and large panels ranges from 100 to 340 watts. The voltage output is DC volts and not AC volts, which is what your household uses. We need a means of dealing with this DC issue, which we'll discuss a little later. Panels are not a complete system. They do not operate without high power electronics to extract the power. To understand this better, let's look at some of the characteristics of panels. PV panels have a nonlinear voltage current characteristic. I have plotted a representation of a panel's current characteristics and the panel's output power versus the voltage. The panel current is the red line and power is the blue line. The vertical arrow on the left is current and ranges from ISC down to 0. ISC stands for short circuit current. Short circuit current is the maximum current that the panel is capable of. ISC occurs when the voltage is 0. Since power is voltage times current, having 0 volts means that the power equals 0. Not very useful. When we say that a circuit is in short circuit condition, we mean that there is little or no resistance between the positive and null or ground. If V equals I times R and the voltage is a constant 120 volts AC and the only resistance R we have is the small loss in the cable, then the current tries to reach its maximum. The horizontal arrow is voltage and ranges from 0 volts to VOC. VOC means open circuit voltage. Open circuit voltage occurs when there is no connection in a circuit for the current to flow. The voltage between positive and return in the panel reaches its maximum. Both ISC and VOC conditions are opposite ends of the spectrum, and they are both useless when you are trying to get power out of a panel. Remember that P equals V times I. When either V or I are 0, then power equals 0. We can see that the current in a panel, represented by the red line, can operate from the maximum short circuit current to 0 at the far right. In order to extract useful power, we need to operate the panel between these two extremes. In order to get usable power out of a panel, you need to complete the circuit. The current in the positive terminal wants to flow to its negative terminal, but it can't because the resistance between the two terminals is too great. So we create another path for the current to flow out of the positive terminal of the panel through some resistance and back to the negative terminal of the panel. This may sound strange to anyone unfamiliar with electricity, but your house appliances perform the same function. The current in an electrical panel wants to flow from the positive load terminal to the null or return terminal, but it can't. The path that we create is through a breaker, through the wires in your house, to an electrical outlet in your living room. If there is nothing in the outlet, then no current can flow. Now, if we plug a lamp into the outlet and turn the lamp on, we are completing a circuit. The electricity now sees a path from positive to ground, even though it's a long one. With the lamp on, the current will now flow out of the positive side of the outlet, through the positive side of the lamp wire, go through the light bulb, which has a resistive element, and back down the negative side of the lamp wire into the return side of the outlet, through the house wire back to the null in the electrical panel, completing the circuit. In this example, the resistance of the light bulb controls the amount of current flowing through our completed circuit. Remember the formula V equals I times R. Because the voltage is constant at 120 volts, a higher resistance means a lower current. Lower resistance means a higher current. A 100 watt light bulb has a lower resistance than a 45 watt light bulb. In practical terms, a 100 watt light bulb is brighter because it has a higher current. Using the formula P equals V times I, or power equals voltage times the current, because we have a constant voltage of 120 volts, if the current goes up, then the power goes up as well. Back to panels. Look at the current line in red. As it moves to the right, the current drops very gradually as the voltage goes up, then suddenly plummets to zero. For maximum power, we need to find where the current times the voltage yields the highest power. The PV panel's maximum power is highlighted by the black circle. The current and voltage for maximum power are indicated by the two dotted lines. An important issue for us to be aware of is that many things can cause the panel characteristics to change all day long. The angle of the sun, temperature changes during the day, clouds moving over the panels, shadows from chimneys or trees as the sun moves across the sky, as well as dirt accumulating on the panels. With the constant changing characteristics, how do we keep the PV panels operating in this highlighted region for maximum power? We can control the current by varying the resistance in the circuit, and this function is called MPPT, or maximum power point tracking. MPPT is performed by the solar inverters, which are connected to the panels. These are some popular brands courtesy of Clean Energy Reviews. Besides MPPT, the function of the solar inverter, or PV inverter, is to convert the variable DC output of solar panels into AC so that the electricity can be fed into a commercial electrical grid. In North America, the output is 240 volts AC at 60 Hz. In Europe, the output is 230 volts AC at 50 Hz. The current will vary with the outputs from the panels. PV inverters also provide anti-islanding protection. Islanding is when a generator continues to provide power when the electrical grid goes down. A grid-tied PV inverter is required by law to sense when a power outage occurs and shut itself off. This is called anti-islanding protection. Without this protection, the inverters would feed the grid wires with live current, which can be dangerous to repair crews. Compared to the wires from the grid, there are only 3 wires coming from the inverter. In North America, the inverter wires are connected to L1, L2 in the panel through a breaker, and earth, which requires no breaker. There is no null wire, as the null voltage is handled by the electrical panel itself. In Europe, the 3 wires from the inverter are connected to load and null through a breaker and earth. A much simpler connection. We will continue to discuss other components used in renewable energy systems in Part 3. Thanks for watching.